Okay, boss. Shall we start? Okay. So in the last class, I made a mistake which was corrected by, I don't know what's her name. Okay, yeah, Tate, and he corrected after that. You asked something, yeah. Right. It's okay. So, mm, uh, it didn't, it didn't get into my mind. It's okay. So, yeah. So in the last class, I said something which is actually not true. I said the following: if some f is continuous, f from x to y is continuous at x naught. I mean, you might be knowing, but since I made a mistake, I'm just correcting it. Okay. So this is equivalent to, I said, if you have if you have a for u with f of x naught, f inverse u is open, I said, which is not true. It just actually what is true is for u for this there exists a maybe, I mean, there exists a v, or it's an open ball or something, v with x naught in that, such that v is contained in f inverse of u. Okay? This is what it says. Okay. To this, we have the corollary. If from x to y is continuous at all points, okay, then f inverse u is open, which is equivalent to continuous. I mean, continuous means continuous at all points, is open. F inverse u is open for all u. Okay. That follows from this, because you can take any point and you can take that. But this is true, and that's what open means, and I think you can see. Okay. So this is, I mean, this is what I wrote was exactly not correct. This is the right statement. So today we will discuss, possibly you might have seen it before, but so we'll discuss completion, and not completion, completeness. Okay. Completeness of a metric space. So we have a metric space. You know what a completion is. Complete. You know what it means by completeness. So X is complete. A metric space is complete if for all Cauchy sequence there exists a X in X such that Xn converges to A in this metric. And I know I hope all of you know what a Cauchy sequence is. Cauchy sequence means it is after some time the distance between any two element in the sequence is less than epsilon. Okay, so Cauchy maybe Cauchy if epsilon greater than 0, for epsilon greater than 0, there exists a n such that d of xn xm is less than epsilon for all n and m greater than or equal to n. Okay, this is the definition of Cauchy sequence. And if every Cauchy sequence has a limit in that metric space, it's called complete. Okay. So this completeness is not a topological property, in the sense that it depends on the metric. So two metric may generate the same open sets. That means it generates the same topology. Still, a sequence may be, it may become the metric space may be complete with respect to one metric, and it may not be complete with respect to the other metric. Okay. So, for example, and let's first talk about this example and go to the n with discrete metric, or n with d1 of nm. This is same as discrete metric. Okay, doesn't matter. I mean, you can take nm, the distance between nm equal to 1 if they are different, and 0 if they are same. So they both will give the same topology. Then all sets are open sets here. Okay, all subsets are open sets. Singletons are open, so all subsets are open. Okay, and n with this set d of nm, maybe d2 of nm equal to 1 by n minus 1 by n. So here also singletons are open. So since singletons are open, I mean both generate the discrete topology. Discrete topology means topology of all subsets. Okay, because singletons are open. Okay, I mean after some time, if you take any point here, any n, so the next one is n plus 1 or n minus 1. So if you take something less than that, then I mean it will be open. It will contain only the single point. You take the open ball around anything sufficiently small, it will be there, right? It will be just 1 by n minus 1 by n plus 1. That will be the least distance. So it will, if it is, this is anyway discrete. The whole metric space is discrete. Okay, discrete metric means all subsets are open. So if singletons are open, all subsets are open because any union of open set is open. So, on this n, I mean, in general, if you have a discrete topology, means all subsets are open. Any general set X, you have this metric, no, d of xy equal to 1 if x not equal to y, equal to 0 if x equal to y. This is a metric. This will give all subsets. Okay, this is what discrete topology. All subsets are open. The power set. Okay. Okay. So a sequence in discrete topology converges. Converging defines the topology. Convergence, I mean, convergence will determine the closed set, so it will determine the open set. So convergence will determine the topology. Okay. So xn contained in X converges in D1 and D2 if and only if xn equal to some constant after some time. After some, I mean, it is eventually after some n, after some big n, xn, xm, they are all ones, I mean, xn equal to some c, xn equal to x naught in x or something. Okay. After some time, it is a constant. Okay. It's supposed to be a constant sequence. I mean, finitely, many things doesn't matter in a sequence. So it's supposed to, it's a, more or less a constant sequence. Eventually, constant sequence are the only convergent sequence. But in D1, xn is Cauchy, the sequence is Cauchy, if it is eventually constant, right? Right? If something is Cauchy, after some time, distance between xn and xm should be, I mean, less than epsilon. But the minimum distance will be 1 or something. So it will be less than epsilon means it will be a singleton, so it has to be constant. Okay. So if it is a Cauchy sequence, if xn is a Cauchy with respect to, I mean, I forgot to write, with respect to D1. Okay. The sequence is Cauchy with respect to D1, if and only if it is a eventually constant sequence. On the other hand, you take this sequence n, okay, xn equal to n, this sequence, okay, is Cauchy in the D2, right? Xn equal to n, the distance between them will be, I mean, distance between xn and xm will be 1 by n minus 1 by m, okay, which will go to 0 as n and m goes to 0. N and m goes to infinity, right? No, topology has nothing to do with Cauchy sequence. That's what I'm saying. So if you study topological space, you will not define Cauchy sequence with respect to topology. Cauchy sequence are defined with respect to metric. It's very specific to a metric. Okay, so that is what I'm saying. You have two metric, they generate the same topology, discrete topology, but you have a sequence which is the xn equal to n. This is not Cauchy with respect to D1, but it is Cauchy with respect to D2. It will converge to infinity if you include infinity. N union infinity, you have to define a topology. Okay, I mean, it will converge in the n union infinity. You will study later. N union infinity is like compactifying n. So in that it will converge to, instead of then, I mean, set is just a set, no? So you can consider just 1 by n union 0. It is same as this. Okay, but it is just a, with respect to discrete topology. Yeah. Something converges either in D1 or D2. I mean, I mean, by this I mean the convergence in D1 and D2 means exactly this. That's what I mean. It's not about a statement about a sequence. It's about the, no, it depends on D1 and D2. If it converges in D1, that means this. If it converges in D2, that means this. If it, I mean, you are worried about the state. I mean, Xn converges in D1 or D2, okay, is equal to this. By and I mean that both, I mean, for both the topology, it is, this is what it means. That's what I said. Here, if it is Cauchy, in the first one, it has to be a eventually constant sequence. The second case, here is a sequence which is not constant, eventually constant, but it is Cauchy, right? D of Xn, Xm. What is complete mean? There's no complete mean. Both are not complete. Both are not complete. No. Sorry, one is complete. Sorry, first one is complete. First one is complete. Yeah. Sorry, first one is complete. But second one is not complete. They have the same topology, but it's not complete. Okay, so this is what. So n with D1 is complete because something is a Cauchy sequence means it's eventually constant sequence, so it is convergent. Okay, n with D2 is not complete. Okay. Okay, fairly easy thing. So the point is Cauchy sequence or completeness is depends on the metric. Okay. So this exercise I have posted assignment. So please look at the module. Okay. I posted a set of assignment. So maybe you can include this. Okay. This is assignment. You have a DXD is a metric space. Okay. Any metric space. Then we have defined this metric rho is equal to D by 1 plus D. Okay. I mean D of XY equal to this. Okay. Then show that Xn is Cauchy. Maybe I didn't show up in the class that this is a metric space. So this is a metric space. Okay. Show rho of xy, which is very easy actually. You just have to use the fact that this is an increasing function. T by 1 plus t is increasing function. That's very clear. Yeah, this is an assignment, class assignment. Okay. So xd is a metric space. Rho xy equal to this. Show that it is a metric space. So is a metric. Okay. And show that xn is Cauchy with respect to d if and only if xn is Cauchy with respect to rho. Okay. So if xd is complete, then x rho is complete. X rho is complete, xd is complete. Okay. That's what it means. And showing that it is a metric just means that this is an increasing function. We can easily show. Okay. I mean, you just write it. It is an increasing function. So you can show that you have to only verify the triangle inequality. So dxy less than dxz plus, I mean, that you can use the increasing function, but you will have something in the denominator which you can, by increasing it, you can remove it. Okay. So the next one I want to talk about is R is complete. I want to show that R is, we have constructed R as a completion of Q. Okay. So I will define a completion of a metric space. I will give two construction of completion of a metric space. The first one is this. Okay. And which actually I have given part of it as assignment. More or less the same proof will work here. So I will go a little bit fast. Okay. Completion of a metric space. So this is a construction. So this is just if you have a metric space, you have an embedding. So let me write the definition. Okay. XD is a metric space. Okay. Then X bar, D bar is a completion of X if there exists, I will define what an isometry is. I will define it below. Okay, free from X to there exists, if there exists a phi from X to X bar, an isometry such that phi of X in X bar is dense, and X bar is complete. Okay. This just says that X sits inside a bigger metric space X bar. Okay. Such that, I mean, sitting means, I will just write a function phi from X to Y is isometric if it preserves the distance. If d of d, I mean, there is d1, d2, I write d for both of them. Okay, so I hope it's okay. Okay, so d of, maybe you should write, okay, maybe x1 d1 and x2 d2. Okay, phi from x d1 to y d2. Okay, so d2 of phi of x, phi of y equal to d1 of xy. Okay? It is just a map which preserves the distance, preserves the metric. Okay? Distance between phi of x and phi of y is same as distance between x and y. Okay? And any isometry will be a injective. It will be 1, 1, right? So if it is 1, if 1, 1 means what? Phi of x equal to phi of y should imply x equal to y. Phi of x equal to phi of y means this is 0. So this is 0. That means x equal to y. Okay? So any isometry is 1, 1. Of course, it need not be on 2. So you have a isometry. So by a completion means you have an isometry from X to another complete metric space. X bar is a complete metric space, and you have an isometry from X to X bar. Okay, which is I mean, where the phi of X, the image sits as a dense subspace. I didn't say what is dense, so I will say what is dense. I haven't defined what is dense. You have seen all these completion and other things, the last course. You have seen it, okay, in full detail, or was it an exercise? In full detail, everything. Okay, let me give the detail. You tell me whether you have seen. Huh? It's okay. Let me say one by one. Huh? What? Yeah, in the second course. Did you see?
I don't know what the full detail.
Okay. So this is what is called completion. Okay. This is what is called a completion. There exists a completion. That is the completion of real rationals. I mean. Okay. Okay. So this is the theorem. There exists a completion. Maybe there exists a unique completion. There exists a unique. I should define. I mean, huh?
Does it have lots of pair of points or just a single?
It's a function so that it preserves the distance between them. That is what is parambar. Phi is a function from x to x bar such that distance between phi of x and phi of y. Phi is defined for only a single point. No, where is pair coming? Distance is for a pair. Yeah. D2 of phi of x and phi of y. There is no pair. D2 is for a pair. Phi is for a single point. Okay, there exists a unique completion. This unique part I will come later. Okay. Before that, I will do for any metric space. So unique, by unique, I will define. Before that, I have to define what is dense, right? So you know dense. Yes, contained in some A is dense if S bar contains A. I mean, the thing is, usually S should be equal, I mean, A should be equal to S bar, but it may not be closed. So we have something like that. This is equivalent to saying for any X in A and R is greater than 0, BXR intersection S is non-empty. Okay? Is not empty. Every open ball around any point in A should intersect with S. Okay, it will be same. You can verify that this is same. Okay? Since you said you have, since you say you have seen all these things, I'm sure this is a easy exercise. Okay. So this is what a completion is. You have a metric space, you have another complete metric space, and you have an isometry where you can embed whatever. This is what is called an embedding. Where in general, if you have two structure, if you have one set and another set, if they have the same cardinality, same number of elements, if there is a bijection between them, we can identify those two sets. There is no difference between set of apples and set of oranges if you don't have any other structure on that. If they have just some n element, those two sets are same in mathematics. So if we have a vector space, if we have a bijection between them, which is also linear, which preserves the linear structure, everything, then we can treat them as same vector space. If we have a normed vector space, if it preserves the norm, which is again an isometry, then we treat them as the same normed linear space. So the same thing is true for a group or anything. If we have a isomorphism, which is also a homomorphism, then we can identify those two groups. So like that, if we have two metric space, I mean here it's metric, if we have a topological space, then it is homeomorphism is enough, continuous function is enough. But here we want to talk about the metric space also, because completion is a metric property. So you have a metric space and the metric is preserved. Okay, that is what an isometry is. Okay. So there exists a unique completion for any metric space. Okay. So here is the proof. As you know, so you define x tilde equal to all Cauchy sequence. Okay. Xn in n equal to 1 to infinity, Xn in x, and Xn is Cauchy. So you take all Cauchy sequence. Okay. Same thing we have done. So this proof should convince you that R is also complete. Not exactly, there is some difference, because in R we use the distance coming from, I mean, initially the distance is defined for rational, then we define a distance for R, but that will take the distance will be an element in R. If you take the modulus, that will give an R. There is a slight subtlety, but it's okay. Okay, I mean, this is enough for us. Okay, okay. So you take all Cauchy sequence in the metric space, and you define Xn equivalent to Yn. Of course, if d of Xn, Yn, this sequence goes to 0. Okay, clearly this is an equivalence relation. Okay, Xn is equivalent to Xn, Xn is equivalent to Yn. Triangle inequality will imply that if Xn is equivalent to Yn, Yn is equivalent to Zn, Xn is equivalent to Zn. Transitivity, I mean, symmetry, everything will be implied by the metric properties. So this is clearly an equivalence relation.
Where we constructed the real number, we defined the same definition.
We use the same definition. We started with Q. We have modulus, which gives the distance, except that the distance will be taken in rationals. Then we define take all the Cauchy sequence in rational, and I mean that is what is R is with respect to this sequence, same equals. Yeah. So now you define x bar equal to x tilde quotiented with tilde. Okay. So two things are equivalent if this has only equivalence classes. Okay. Now you define D of any equivalence class of Cauchy sequence. Okay. You have equivalence class of Cauchy sequence that you have to verify this is well defined. D of Xn Yn. Okay. You have an equivalence class. So you had X, from that you took all the Cauchy sequence in X, then you quotiented with respect to this equivalence relation. So you got X bar. On this X bar, you define the distance between two equivalence class of Cauchy sequence. You pick an equivalence class, you pick one sequence. In this equivalence class, you pick one sequence, then you define this. Now you have to verify this is well defined. To verify this well-definedness means there are two things to verify. It exists and it is well-defined. There shouldn't be two values for that. Okay, limit n going to infinity. So well-defined. I hope it is. So this is what I mean. You did all these things. Huh? It's clear to you? It is Cauchy. First, you have to verify that this limit exists. For that, you have to verify this is Cauchy. Okay, to verify this is Cauchy, you have to verify Tn xn yn minus Tm xm ym. Okay, this goes to 0. But then triangle inequality will tell you that this is less than or equal to d of xn. We have to get xm here. I mean, that's the right thing to get. So once you get xm here, then d of xn yn minus d of yn xm, okay, plus d of yn xm, okay, minus d of xm ym. Okay, this is equal to this. But then these two will give you d of xn xm. Those two will give ym yn. So which is less than or equal to d of xn xm plus d of. I mean, this is the other part of the triangle inequality. Triangle inequality has another version, no? You can take it to the other side and okay, so those two, you want to write it as d tilde. This is what you want? Okay, yeah, good. We call it d tilde. Yeah, it shouldn't be the same d. Okay. Okay. So this exists. Now we have to verify another thing, which also follows from triangle inequality. We don't have anything else. It has to follow from triangle inequality only. So what you have to verify? We have two sequences xn and xn prime, both are equivalent. Okay, I mean two sequences which are equivalent, let's say, and we have yn which is equivalent to yn prime. Okay, then we have to prove that. Need to prove this limit. I mean, we have to worry about the limit only. Limit xn yn is equal to limit d of xn prime yn prime. Okay, this is what to verify well-definedness. Well-definedness, first such a thing exists, the limit exists because it's a Cauchy sequence. This is a Cauchy sequence, so the limit exists. The next one is you take two different elements from this is defined for an equivalence class. So you take two different elements from the equivalence class, you should get the same value. So that is what this means. Okay. So again apply the same. You have xn yn. Okay, that is less than or equal to, as you can see, we want to apply the equivalence. So this will go to 0. So d of xn prime and xn prime yn prime, let's put, and then d of yn prime yn. Okay, this will go to 0, this will go to 0, we have this. On the other hand, this will be less than or equal to, I mean, here there is nothing about xn and yn. You can do the same thing with d of xn prime, yn prime, with xn yn here. So they will have the same, this is clear? The same inequality with xn replaced by xn prime, yn replaced by yn prime, you will get another inequality. Those two inequalities from high school mathematics will imply that these two have the same limit. Okay, this is an exercise. Okay, so this is well defined. Okay, so the metric is well defined. So we have got a metric which is well defined. What is next? We have to verify that it's a. So we have verified. I mean, this is a Cauchy sequence. So this implies x bar d tilde. I said d tilde. I call it d bar. Okay, it's better. I call it d bar. Okay, d bar is a metric space. Okay. Now you define phi from x to x bar. Okay. So phi of any x is just xx, constant sequence. Constant sequence is a Cauchy sequence. So it just sits inside as a constant sequence. Okay, that's right. Now you want to verify that, I mean, it is clear that phi is an isometry. Okay. D bar of phi of x, phi of y, it is just a constant sequence. That will have the same limit, right? D of xy, which is the limit of d of a constant sequence xy, which is same as that. So clearly we have that it's an isometry, which is clear. Phi I have defined to be this. If you have a x here, define. Yeah, it should have. Yeah. It will be more. It should map equivalence class to. Correct. You take this and you take the equivalence. This is what you mean. This is what you mean. Yeah, correct. Yeah. It should be equivalence class. Okay. Yeah. So now you want to verify that this is dense there. I mean, it's isometry, which is clear. Now to prove phi of x contained in x bar is dense. Shall I leave this as an assignment? These things. There is something. Okay. Okay. So this is. I mean, for this you have to take a Cauchy sequence. Take something in x bar, which is a Cauchy sequence now, which is something in the, of course, equivalence class. But you take an xn. Okay. Now you have to. I mean, now this is all Cauchy sequence. Now you have to get something here. Okay. So you just take it. So given epsilon, so this is something you have to verify a little bit. Given epsilon greater than 0, choose some xn such that this xn, I mean d, I'm writing modulus, d of xn, this is Cauchy sequence, right, is less than epsilon for all nm greater than or equal to n. Because it's a Cauchy sequence, you can choose this xn. Okay. See, okay, rather than writing this, I mean, I have written it, but instead of writing epsilon and other thing, which may get confused, directly I will write it. What I do is the following: you take, so I mean, you have a Cauchy sequence here. You want to get something in phi of x to approximate that, right? So you take this sequence itself. So if define, I call this as xk rather than xn. Because I want to call this as, I mean, I want to vary, I change to xk, okay, so that I will use n here. Okay, you choose phi of xn, okay, equal to some, wait, let me make the notations clear. Okay. Yeah, thank you. So let x bar equal to xn, okay, a Cauchy sequence. Okay, now and let xn bar equal to just this phi of xn. This is okay. This makes sense. X bar equal to maybe xk. Okay, k equal to 1 to infinity. X bar is an element. Okay, is in xk. Okay, in x. Okay. Now you take xn bar equal to phi of xn. Okay. Now I want to say that this phi of xn converges in this. Now d of phi of xn, I mean d of xn bar, x bar, okay, that is equal to d of phi of xn, x bar, okay, which is equal to just d of xn k xk limit k going to infinity, right? By definition, d bar. Yeah, I'm repeating. I'm forget about this. From here, I'm xn bar, which is a sequence, which is just the constant sequence phi of xn. Phi of xn is just a constant sequence, right? Phi of x is constant sequence. X bar is, you take a Cauchy sequence. I mean, you have to work with equivalence class, but it's okay. You take a Cauchy sequence xk, okay? Then I take the nth element, take the constant sequence corresponding to that, call that as xn bar, which is a sequence now in x bar. Okay? Now I have to show that this converges in this metric. So d bar of xn bar and x bar is just limit k, I mean, which is just the distance between them, So which is limit k going to infinity xn xk bar. Okay. Now if for Cauchy sequence, for a sequence to converge, you have to take limit n tends to infinity. Now you take limit n tends to infinity, which is just equal to, I mean, the same limit n tends to infinity. Limit n tends to infinity, k going to infinity, n going to infinity, this goes to 0. That is what the definition of Cauchy sequences. So you don't need epsilon delta, you can directly write it. Okay. I mean, epsilon delta, all these arguments are inside that. Okay. I mean, of course, you have to use that. But since we know all that, Cauchy sequence means xn, d of xn, xm converges to 0 as nm goes to infinity. Okay, I'm just using that definition. Okay. So these things implies that phi of x contained in x bar is dense. Okay. So what else is there? Only uniqueness I have to prove, right? That's all. Uniqueness, I will come to this later. I will come to this after some time. Okay, so I'll go there. Okay, so I have to prove something to prove uniqueness. So that's why I'm postponing it. Yeah, I'm going to do that also. Okay. Huh?
Okay, we showed that limit n tends to infinity of d x n bar xn
Yeah.
x bar is equal to 0.
Mm.
So, but what did that show exactly?
That shows xn converges to xn bar converges to x bar in the in that x bar. I mean, it should work for other elements in the equivalence class also. It is enough to show something in this equivalence class converges something in the equivalence class. Exactly. It is.
Phi of x is
This is in phi of x, no? This is phi of xn. Xn bar is phi of xn. So you have a sequence in phi of x converging to that, right? If you notice, we are actually using the completeness of R here in some sense. So, but then, so we have to separately prove for R. Okay, that's what I was saying, the subtlety about it. I will come back to that later. Okay. Okay. Okay, maybe I will separately prove for R is complete later. Okay. So this is examples. I will come back to this. R is complete. It is just a bit messy. I don't want to go into that now. I don't remember. I don't remember every detail. So it's a little bit messy. Prove completeness of R. R is another. R is one complete space. Of course, if R is complete, we know R and C and C, R and C and they are all complete because if something converges, coordinate with converges, something converges, both real imaginary part converges, because of all that, they are all complete. Okay. So next example, better non-trivial example is if S is any set, then B of S is complete. You know the proof of this? You have seen many things. Do you know the proof of this? B of S is all bounded sequence. All, I mean, this is all those F from S to either R or C, doesn't matter. We can take C if you want, or you can take R if you want. Okay, bounded sequence. I mean, F is bounded. Yeah.
this set will be there such that its completion is
You take rationals. I mean, you take
qn plus I
Qn plus IQn. Yeah, yeah. There can be many sets.
This is not unique.
Anything can be dense in something bigger. There can be so many other sets which can be dense in something. No?
No,
Completion is C, which is unique. You are asking about whose completion is this. That can be many things. No. I mean, a subset can be anything, right? A subset which is dense can be anything. It doesn't come in one form. It is just the superset, which is the completion is unique. This is with respect to supremum metric, right? We have defined norm of F infinity equal to supremum of mod of S in S. Okay? All bounded sequence. Okay, this is complete. Okay? You know the proof of it. Okay, proof. Okay, It is just says that you take set of all bounded sequence with respect to uniform convergence, it is complete. Okay. So suppose Fn contained in it is with, I mean, the supremum, this convergence is uniform convergence, right? F1 converges to F if supremum of S in S, f of S, Fns minus f of S goes to 0. This means given epsilon, you can find a n uniformly for all of them because the supremum will be less than that. So uniform for, yeah. What is f is a function. What we, the B of S is complete, where B of S is, you want like this, right? First I wrote this, then I wrote that. That is the problem. B of S is equal to this is complete. Were you taking notes? Then you may be looking there and yeah. So I said that B of S is equal to this, which is complete. Now it's okay. B of, we defined this in the first class. This is a metric space, examples of metric space. So the B of S is equal to all, either you take C or this, okay? Don't get, there is no quotienting or something, okay? C or R, okay? All complex valued functions means it's a complex vector space. Real valued function means it's a real vector space, okay? Then B of S, all bounded function from S to something. You can actually take it to a non-linear space and give the same definition. Okay? Wherever you can talk about boundedness in the range. S is just a set. There is no other structure on that. But on the range, if you can talk about boundedness, okay, even a metric space is enough. Okay, then you can define this set. There are some generalization of that. Yeah. What? Supnam? No, this is taking values in C and R, no? There it is defined.
No, if it was a different metric, what will be the metric?
What will be the metric on in a non-linear space? You can take the norm of that. So other things in a metric space, you can't define the norm. Yeah, you can't define the norm. Yeah. I mean, no, you can't define the norm on a metric space. Yeah, for a non-linear space, not on a metric space. I am saying this can be generalized to a non-linear space. Need not be C or R. You can take a non-linear space and do it. That's all. Okay. So now this just convergence here means uniform convergence. Okay. So now we want to prove that this is complete. Yeah. Where here are there? I mean, some time back I was saying that Fn converges to F uniformly means that. I mean, Fn converges in this topology means it converges uniformly. I was orally saying and then erased. That's not part of it. Okay. Now Fn is bounded functions. No, I talked about sequence. Now I am taking to no, we want to prove that it is complete. For that, we have to take a sequence, which is Cauchy. We have to find a limit. So that's what I'm doing. You have defined B of S, and the claim is B of S is complete. I'm giving a proof of that. Okay. So proof is Fn in B of S is Cauchy. Okay. We have to find a limit. Okay. It's Cauchy means this is Cauchy in this metric. That means given, I mean, that just means Fn converges to F uniformly. Or you can write that supremum of F of Fns minus F of S goes to 0. Okay? Supremum of S in S. It converges in Fn is Cauchy supremum of Fn minus Fm as Nm goes to 0. Okay. So supremum goes to 0. This implies each Fns, okay, is Cauchy. This is contained in RRC. Okay, is Cauchy. Okay. For each S, this is Cauchy. since our real line and complex number are what they are complete, okay, there exists, there exists some Fn s converges to Fs. So Fns converges to some f of s in R or complex number or real line. Each Fns is Cauchy, so there exists a limit for that. Call that limit as f of s. Okay, that is well defined because the limit is well defined. Limit is unique. Because Cauchy, there exists a limit because it's a Cauchy sequence, and the limit is unique, so it's well defined. So you have to remember all that. So Fns converges to f of s, which is well defined. Okay, f of s converges to f of s. Now we need to prove two things. Oh my God, what's happening? Can someone read it to me? Sorry. That also maybe. Sorry about it. Thank you. Okay, now we have to verify two things. So I've taken a Cauchy sequence. I use that this criterion, Cauchy criterion. Then for each s, this converges. So I have got a limit. I defined that f of s. Now I have to prove that this f of s is in b of s because I have to find a limit in that. Second, I have to prove that this Fn actually converges to f uniformly. There are two things I have to verify, right? Okay. So to prove that it is bounded, f of s, you have to take the modulus. Okay, you have to show that this is bounded by some number, but this is less than or equal to, let me write it, f of s minus some Fn s plus some Fn s. Okay. Maybe I call it Fn, I call it some fixed number, okay, some Fn naught for any n naught. This is true, of course. This is just triangle inequality, which is true for any n naught. And I write something here, limit m. Okay. Modulus is a continuous function, so I can put a limit here and I can put a limit here, right? Fms converges to f of s. Okay, so this will go to f of s. I put a limit here, I put a m here. If you take limit here, this will become f of s. That's what I initially wrote. F of s is less than or equal to this. I put a limit here. What's wrong? There is nothing, because that's going to converge to that. Okay, limit Fms converges to this, and I can put any Fn naught. Okay, now after given after some n naught, or you can keep it n. It doesn't matter. Okay, and we fix an n naught. Okay, this Fn naught is bounded function, so there will exist a m for this. So this m after n naught, after some time, this is going to become, so now that is less than or equal to supremum. You can write the limit. You can take the limit outside, limit m of f of Fm minus Fn naught is infinity plus norm of Fn naught. Okay. This is okay. Okay, and this is less than epsilon after some time. So the limit will also be less than epsilon. This is something, a bound for this. Okay, this is less than or equal to epsilon plus norm of Fn naught. Okay, so it's bounded. This is a number, single number. I am just choosing a single n naught, some n naught, and write like this. You can argue the whole thing with epsilon and other things, okay, but it's not needed. Okay, I just write it like this. Okay, so then this is some n naught. Any n, some n naught means I will choose an n naught. After that, this will become less than epsilon. Okay, so this is less than this. So it is. This limit anyway exists because it's Cauchy. This limit exists. Okay, which is limit m. This is less than epsilon. This is less than. So this is bounded. Okay, the same idea we will do for this. So this shows f is bounded. Okay, now I have to prove that f and Fn converges to f. So for proving that Fns minus f of s, we do the same thing. Okay, now this is equal to limit m going to infinity Fn s minus Fms minus Fns. Okay, correct? That is of course less than or equal to limit m going to infinity, norm of fm minus fn infinity, right? For all s, for all s. If you want, we are using the fact that norm is continuous or something. No, we don't. No, we are not using. Sorry.
Supremum of s part of s of fns minus fns
Hmm.
to 0.
Hmm.
And then you've written that implies that fns.
No, wait. Let me point out. What is the question?
Third. How does
1,
it
2, 3. This line. Second line implies the third line. The supremum goes to 0. For each s, it will go to 0. What is the problem? Yeah. This is fns minus fms is less than, oh, yeah, fns minus fms is less than the supremum. Mod of f, that's what I'm using again and again. Fns minus fms is less than or equal to norm fn minus fm infinity. Okay. So because of that. Okay. Supremum goes to 0 for each s. Supremum over something, each s is less than that. That's all. So it's all positive. So here I am saying fns minus f of s, which is equal to limit of this. Okay. Now this quantity for each s is less than this. Okay. And I am writing the same limit because this limit anyway exists. So you don't have to worry. Yeah. Now you take the limit n and m because it's Cauchy, this will go to 0. As I said, you can argue with epsilon also. You have to prove that this is less than epsilon after some time. You can carefully choose the epsilon and other thing. This argument is also okay. Okay, we don't have to confuse ourselves. This is all right, perfectly all right. Okay, okay, okay. So we have proved that this implies Fn converges to F in norm infinity. Okay, so it is complete. Okay, proof is okay. Any doubt? Any problem? So this is how one should prove. Okay, okay. I have taken. Okay. So X is complete. Complete. And some A contained in X is complete if and only if A is closed. Should be easy. If it is, no, it's okay. Yeah. I tend to drop more these days, not just here, everywhere. Okay. Yeah. So the original Hilbert's original metric space is complete. Then a subset is complete. I mean, you can restrict the metric to something. Okay, so yeah, and here we don't need to worry about topology and everything because we have a metric. The metric as a function can be restricted, and we get a topology according to that. Okay, so this is complete if and only if that is closed. Okay, that is clear. So if it is closed, then if you have a Cauchy sequence here, that will be a Cauchy sequence on the top one. So there will be a limit because it's closed. That has to be in this. So it's complete. The same thing is true. Sorry, it is this way to true. And this is complete means a Cauchy sequence. It has to be in that, and it's closed. It's all clear. Any complete one is actually closed. Okay, so this is clear. So from this we prove the following proposition. Okay, let me prove for this. Then I come to that something. C01 contained in B01. This is all those continuous functions on 01 with respect to supremum metric. So this is complete. This is closed and so complete. Set of all bounded functions on 01. So continuous functions on 01 is complete. That's what this is. This is closed, so it's complete. Why is it closed? Yeah, uniform limit of continuous function is continuous. So hope you know this. That just follows. There is a little bit subtlety. You have to talk about this. F of x minus f of y is less than or equal to. This is what is called epsilon by 3 trick. F of x minus fn x for any n, maybe fn x or n naught or something. Fn x plus fn x minus fn y. I mean, I'll just write it for arbitrary something. Then it will be clear. So by f, I mean, I just want to leave it as exercise. I'm just giving you the argument. Okay. Then f of fn y minus f of y. Okay. Suppose, I mean, you want to show that C01 is closed. That means you take a sequence here. Okay. Suppose if it converges to something, see, this is the better thing. I mean, here we have to prove complete means you have to prove that you take a Cauchy sequence, you have to find element. Here you don't need to do that. You take a sequence which actually converges to something, some bounded function, then you have to show that it is actually continuous. That's what you have to show. You take a sequence here, it converges to some function, you have to show that that is actually continuous. So to prove that continuity of f, okay, fn converges to f, fn are in C01. Okay. Then you have to prove that f is also in C01. So for that I consider this inequality. After some time, this fn and f will be uniformly close. So that is why you can find the same epsilon for these two. I mean, that's very important. Uniform convergence is important. Otherwise, it's not true. Okay. So you can find the same epsilon for x and y. Okay. Shall I go through this argument? I thought, go through it completely. Okay. We'll take more time. That's all. Okay. Proof. We want to prove C01, which is contained in B01, which is all bounded function, is closed. That's what we want to prove. We have already proved this is complete. Okay. So to prove this is complete, it is enough to prove this is closed in that. So I take a sequence Fn contained in C01. Okay. And Fn converges to some F in B01 in norm infinity. Okay. In this norm, then we have to show that f is in C01. That's what it means by it is being closed. Okay. So to show that f is in C01, we want to prove f is continuous. So that's why I wrote this inequality, f of x minus f of y. So now you choose, given epsilon greater than 0, choose n such that f of x minus fn x, sorry, now I take the supremum. Supremum of f of x minus fn x is less than epsilon by 3 if you want. Okay. Okay. So for any x and y, this is true. Okay. On the other hand, this fn, n is fixed now. That is continuous. Okay. So I'll write here. Now you have this inequality, f of x minus f of y, okay, is less than or equal to f of x minus fn x minus fn x minus fn y plus fn y minus f of y. Okay. Now this is less than epsilon by 3. This is less than epsilon by 3. Okay. Now given epsilon by 3, you choose a delta such that if d C01, no, so it's okay. So if x minus y is choose delta greater than 0. So if x minus y is less than delta fn x, this is continuous. So you can do this. Okay, fn y is less than epsilon by 3. Now this is less than epsilon by 3. This is less than epsilon by 3. So the whole thing is 0. So this is okay. You can write the rest of the argument. So it's very, I mean, the subtlety is you can approximate both these things when x and y are arbitrary. For any two different arbitrary x and y, you can have the same n. Okay? If it is not uniform convergence, the n will be different. This will not work. Okay, so That is, so uniform limit of continuous function is continuous, because of that is closed, right. So what about this? All continuously differentiable functions. Example, C101, which is of course contained in C01, which is contained in B01. Okay, is that closed? This is complete, we know now. But this is that closed? It is not closed, right? This is dense here. Okay, of course there are continuous functions which are not differentiable, but on the other hand this is dense here, so this cannot be closed. Why is it dense here? Differentiable functions are dense in C01, right? Continuous function. All polynomials are infinitely differentiable. In fact, infinitely differentiable functions are dense here. Polynomials are dense here. Weierstrass theorem, which says we will prove Stone-Weierstrass theorem, which is stronger than that. Okay, so that will follow. So C1 is dense here. Okay, polynomials are dense. We will prove. You must have seen, or we will prove it later. Stone-Weierstrass theorem. You haven't proved. So we will prove that we will not use Weierstrass theorem. Okay, we will prove Weierstrass. All we need is we have polynomials converging to square root function, which we will construct explicitly. Using that, we will prove Weierstrass theorem. Okay? So we will not use this. So for the time being, you accept Weierstrass theorem. So that will prove this. On the other hand, C101, okay, with norm F1 infinity, which we have defined, which is equal to norm F infinity plus norm F prime infinity, is complete. Okay. Okay. I mean, this is a statement. I will give you a proof. Okay. So C1 with the uniform norm, infinity norm, C101 with uniform norm is not complete. But with respect to this norm, 1 infinity norm, which we defined like this in the first class, this is complete. Okay. That is because proof. That is because of what? You must have seen this theorem in calculus. If F1 converges to F uniformly and F1 prime converges to some G uniformly, then F prime should be G. Okay. F1 converges to F. These are all, I mean, you have F1, these are all in C1, differentiable function. Okay. F, which is in C1, which is in C. F1 converges to F. Okay. And F1 prime converges to some G. Then F prime is equal to G. You haven't seen this? This is some of the basic theorem. Yeah, everything is continuous. Okay, F, G, everything is continuous. This is converges to this in uniform. I mean, that's what it converging in this norm, no? Convergence in this norm, F1 minus some F minus F1 goes to 0. That means F minus F, this goes to 0, F1, F prime minus some F1 goes to 0. Okay. So Fn, let's start with this. Fn contained in C101. Okay. And I mean, suppose if it is something is Cauchy with respect to this, okay, is Cauchy. Okay, with respect to norm 1 infinity. Okay, if it is Cauchy, that means Fn, I mean, that means Fn prime, both Cauchy. Okay, in C01. Is that okay? I'm saying that Fn is a sequence of differentiable function C101. Okay, I have a differentiable function, sequence of differentiable function that is Cauchy. Okay, in this norm. Okay, F1 infinity, okay, infinity norm. That means it is Cauchy in the first one. That means it's Fn is Cauchy uniformly, and Fn prime is also Cauchy uniformly. So they should have a limit in continuous one. So this implies F1 converges to some F in norm. uniform norm, and Fn prime converges to some G in uniform norm. Okay. So that is the statement I made. Fn converges uniformly to F, Fn prime converges to some G uniformly. It will be different. But then we have to prove that all we have to prove is that is differentiable. That's what we have to prove. And this will converge in this norm. Once we prove, all we need to prove it, then F prime is equal to G. I mean, this is a statement. Once this is true, it is done. Right? Okay. So can anyone give me the proof of this? Just it follows from something. You just say something. Even I don't remember. I mean, I think it will work, but I don't remember the correct proof. I have to write. Okay, let me try here. I mean, I'm trying that. Okay, so we have Fn converges to F uniformly. Okay, so Fn converges to F. Then we want to prove that the derivative F prime equal to G. Okay, so I write it like this: Fn S minus Fn T minus S minus T. Okay. Mean value theorem will say that this is equal to Fn prime of some S naught, which is in the interval S and T. Okay, right? Right. Now you take limit S going to T. Limit S going to T, Fn S naught will go to, because it's continuous, Fn S naught will go to Fn, I mean, S to T. So that will go to, yeah, limit S going to T and limit N going to infinity. Okay. No, so the limit, yeah, I think that's what you have to do. Limit S going to T, that will become, S naught will go to T. So that will be Fn prime T. Okay. So, but then this will become, no, that is just, this is just Fn prime T, no? Wait a minute. Yeah, you take limit, let me write. You want to show that this is G, no? N going to infinity, limit S going to T. Is that okay? That will be limit S going to T, limit N going to infinity, Fn prime of S naught. Okay. Yeah, Fn prime is continuous. That's what I'm saying. Huh? F dash of T. You are saying yes or it will not? Wait, I'm just, that's what I'm saying. So, I mean, you have to prove that that is what the limit is. So, limit N going to infinity, I mean, which one? Limit N going to infinity, this is defined, right? So, this will be f of s minus f of t minus f of s minus t. Now, limit s going to t will be the derivative of that if it exists. Limit f, this is equal to f of s minus f and t, f of s minus f of t divided by s minus t. Limit s going to t will be precisely f prime at t if it exists. Okay. So that exists should follow from here. So limit n going to infinity fn prime of s naught will be g of s naught. No, will be g of s naught. So now you take limit s going to t. That is precisely f prime at t. That limit exists. That limit exists. So that's what. This is mean value theorem. Without the limit, you are writing this is equal to this. That is mean value theorem. Fns minus fn t minus s minus t equal to fn prime s naught for something between s and t is mean value theorem. I'm using mean value theorem. Then I am applying these two limits. That's right. That's a good question. But it will give some, that's right. But it will be still between S and T. Okay, so maybe you have a Sn, maybe you call it Fn S naught. Okay. So I am saying that Sn, there is very good. There is a subtlety. So Sn naught will, I mean, it will go on shrinking as n goes to infinity, that will somehow will go to t. So this I should leave it as an exercise. So I mean, it is something like that. You have a sequence, okay, but I mean, there is no other way. It has to go to t only. Okay, this will go to t. This will also go to t. You can write the expression. You can write epsilon delta. Huh? What? S naught is a function of s. S naught is a function of s. I am not writing it here, but it is there. But he is saying it will differ from n. It will differ for each n. But that will go to t only. But then you have a different functions. I mean, the continuity. I mean, you have a sequence of continuous function. There is something is there. I will ask you to write it as an assignment. Okay? This is this is very easy. If you search in the internet, you will find it. But better without doing that, or if you by doing that, you just write the proof correctly. Okay. But I told you mean value theorem is used. Then you use the limit somehow. As he said, correctly pointed out, there is some subtleties here. It will work. Okay. So please do that. So C1 is complete. So today I have some energy. So shall I continue for some more time? Okay. So in the last class, I was tired and stopped before time. Okay. So now we have C01. We had two topologies on this. One is infinity. The another one is C01 with respect to norm 1, right? Okay. This is complete. We have proved. This is not complete. This is not complete. I will not prove. In the sense that involves, I mean, some measurability and other thing. I will not prove that. Okay, this is a much bigger space, which will be what is called L1 space of something, which will be different. I mean, you will have functions which are not Riemann integrable, but I mean, you have to look at that. Okay, so we will not do that. But what I will prove is the following: a set U contained in C01, or we'll use closed set rather than open set. Open set also we can work with, but closed set is easier. Okay, so suppose F contained in C01 is closed with respect to norm infinity. I think it's the other way. With respect to norm 1, okay, then F contained in C01 is closed with respect to norm infinity. Okay. If some set is open, I mean, closed means it's true for open also, okay, by taking complement. So if you have a set in C01 which is closed with respect to norm 1, then it is closed with respect to norm infinity. So you assume F is closed with respect to norm 1. Okay, you want to prove it is closed with respect to norm infinity. To prove something is closed with respect to norm infinity, you take a sequence Fn contained in C01, and Fn converges to F in norm infinity. Okay, convergence in norm infinity will imply convergence in norm 1, right? Uniform convergence. Okay, if Fn converges to F uniformly, okay, then integral Fn minus F will go to 0. Okay, if uniform convergence, you can take the limit inside. So because of that, Fn will converges in norm 1. Okay, but since it is closed with respect to norm 1, this F should be in F. That's what we want to prove. Okay, I mean, if convergence is stronger, yeah, this is okay. Huh? I'm saying that if it is closed with respect to norm 1, it is closed to Fn converges to F in norm infinity will imply Fn converges to F in norm 1. Closed one is the other way. If it is closed with respect to norm 1, if it is closed with respect to this. Similarly, open with respect to that will imply open with respect to this. Converse is not true. You can take t power n, Fn t equal to t power n. This doesn't converge uniformly. T is in 0, 1. Okay. Then this Fn will converge to 0 function, 0 in norm 1, 0 function. But then Fn t pointwise converges to 0 if t is in 0, 1, and Fn of 1 will converge to 1. So it doesn't converge uniformly, so it doesn't work. Fn does not converge just to Fn norm infinity. So this t power n is 0, that is a closed set in that, but that's not I mean, this doesn't work. Okay. So the other way the convergence is not true. Something converges in one norm will not imply convergence in that. Okay. Okay. This is one thing. It will take some time. I want to give another construction of the uniform continuous, completion. Shall I go through quickly? It will take 15 minutes. Is it okay? Huh? Huh? Completion. Okay. Shall I go? You have no problem. Okay. Only you can. Okay. I will just give this construction. Another construction of next time. Huh? Okay. I'll stop. One second.